Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Margherita Talia with us today. Hey, Margherita.
Hi, everyone. And thanks a lot for having me here.
Oh, well, it's really great. It's a really lovely article, and I'm glad we're going to get a chance to go through it. So where are you at?
Actually, I'm in my office in Bologna, Italy.
Oh, okay. So they're letting people in their offices these days?
Actually, yes. I mean, we have just shifted from a high-risk zone from a medium-risk zone. So now we are going back to offices and face-to-face lessons. And
that's great.
So,
that's great.
Yeah, I mean,
I noticed you still have your mask hanging over your left shoulder there.
Yes, I mean, luckily my office mate is not here today, so I don't have to wear it all the time.
There we go. Very good. So let's see, it's April 15th in 2021. So how is we're past equinox. So how is spring in Italy, in Bologna these days?
Actually, not very good. It's been raining in the past 3 or 4 days, so we haven't seen real spring yet.
Okay, coming. It's coming.
And how is it, the weather?
In Phoenix, we are enjoying the last few cooler days. That's relative, right? So let's see, 130, 75. So we got up to about 34, 35 C the other day during the day, but it's dry, so it's still fairly comfortable. In about a month, it's gonna be just hot. We'll be 40 C plus or something like that. So
wow,
just lovely. Okay, it's good. It's good. So Talia, what do you like to do for research?
Well, actually, I love to study galaxy evolution, and in particular the properties of high redshift galaxies. And during the years, I've sort of looked at galaxies from different point of views, so from different wavelengths. So, for example, I started my career studying optical spectra, and now I've shifted to submillimeter and the radio wavelength. So in order to have, let's say, a broad view of the galaxies that I'm studying. So I think it's very nice because I get to learn a lot of techniques and to piece together all the pieces of the puzzle.
So what was the driver to going to longer wavelengths?
Actually, ALMA. When ALMA came out, I mean, because actually I was already studying interstellar medium properties from the optical point of view, and so when ALMA came online, it was only natural to go and see the cold molecular stuff. So yeah.
And that is going to lead us to this very lovely APJ article, Illuminating the Dark Side of Cosmic Star Formation 2 billion years after the Big Bang. And Margherita, take us away.
Okay, so actually, first thing that I would like to say is that this was actually a collaborative work, especially with Margherita Giulietti, who was a master student. She's the third author, and she was a master student of mine, and we worked very closely together for this project. And now she's doing a PhD in Trieste, and she moved to other things, but we are going on collaborating on these galaxies. Great. So actually, the scientific driver of this paper was the fact that I started to become interested in the study of the star formation rate density and its variation across cosmic time, and basically we have quite a clear picture of how how it evolves from the local universe up to redshift 2 or 3, but we actually are not very sure about what's happening at redshifts higher than 3. Because there are some studies, for example, especially based on Lyman break galaxies, that show that there is a steep decrease in the star formation rate density at higher redshifts. But especially in the last years, there have been a lot of some studies based on far infrared and radio selection, which show instead a plateau. So a much higher star formation rate density at high redshift. And so the point is, okay, maybe in the Lyman break galaxies based estimates, we were losing dust obscured galaxies that are only coming out from Herschel, from the submillimeter, and from the radio. So that was let's say the main driver, and also the fact that I mean, for example, especially in the last years, there has been an increase in the discovery of these very dust obscured sources at high redshift. So, I mean, the hypothesis seems to be valid, let's say.
Right.
The point is that if we look at this problem from the far infrared point of view, there are some, let's say, observational limitations, in the sense that the largest surveys in the far infrared were done with Herschel, which has not a very high sensitivity if you go at very high redshift, and also has the problem of a very large PSF. Okay. So basically, yeah, you are you are limited by confusion a lot. So it's very difficult to deblend the sources, especially if you have faint ones. Okay. And ALMA was great in this respect. I mean, so going to the sub-millimeter was really a breakthrough. The point is that with ALMA, we do not have yet large area surveys. So, I mean, we don't have, with ALMA, it was possible to, let's say, discover a lot of these dust obscured sources, but we do not have the statistics yet to derive conclusive statement. That's why we decided to go to the radio. So this, yeah. So basically, what I mean, for two reasons. One was that there was this very wonderful survey in Cosmos, which is called VLA 3 GHz, the VLA 3 GHz survey. So it is a continuum survey at 3 GHz done with JBLA telescope. The PI of the survey is Bernesa Smolcic, and I mean, this is a survey which covers the entire cosmos, so it's 2 square degrees, much larger than any submillimeter survey with ALMA done until today. So we could have a lot of statistics for this reason. And the second reason why we decided to go to explore radio wavelengths was the fact that when you select your galaxies from the far infrared, you have to take into account that your selection may be biased by the temperature of the dust. And I mean, we don't know yet precisely how the dust behaves at very high redshifts. So, I mean, we are making assumptions, but we do not really know. There are some surveys now that are answering those questions, but I mean, we do not know dust at very high redshift as well as we know dust in the local universe. In the radio, you do not have this problem. So, I mean, this is another bonus for the radio selections. There is a con anyway, which is the possible presence of AGN, because of course when you do a radio-based selection, if you have an AGN, the AGN can boost your radio emission, and so you can overestimate the actual ongoing star formation of the galaxy, because there is a close relation between the radio emission and the star formation. But if you have an AGN, a powerful radio AGN, things get messed up.
Yeah.
So, but so let's say that this is probably the biggest possible bias in our research. Yeah. But we tried to use all the multi-wavelength information that are available in Cosmos to establish if our sample was really biased by AGN or not.
Mm-hmm.
And spoiler, it is not.
Yay. So. Yay. Exactly. That's good. Otherwise, we probably wouldn't be talking about this.
Yeah, I think so. So actually, I have to say that the VLA Cosmos 3 GHz survey was also used in 2017 by Novak to derive the radio luminosity function and the star formation rate density. But to do that work, they only used galaxies that had a counterpart at near infrared wavelength, so in the famous Cosmos 15 catalog by Legel et al. 2016. So basically, what we wanted to do was to explore how sources which are usually, let's say the dark sources, so the sources that are usually excluded from the analysis because they do not have counterparts that allow to derive the redshifts, basically. We wanted to understand how these sources, if these sources have a high impact on the star formation rate density at high redshift. So basically, our sample is the complementary one of that used by Novak et al. Okay. So basically, our selection was to start from the small Chich catalog, and then we selected only the galaxies that did not have a counterpart in the near infrared Cosmos 15 catalog. Okay. I'm with you. And we call these galaxies optically dark, UV dark, because it's cool to call dark something.
Yep. Very good.
And yeah, and actually we identified about 500 galaxies selected in this way. But then, this was, let's say, a sort of pilot project in the sense that, we wanted to have an initial estimate of the importance of these dark galaxies to the star formation rate density. So we selected, let's say, a golden sample of about 200 galaxies selected to be reasonably isolated. Because we wanted to go back to the maps to do a photometric analysis, to do a stacking analysis. I will talk about that in a minute. And we wanted to be sure to have contamination by nearby sources down to a minimum.
Right.
So that's let's say, why we analyzed in detail only 200 out of the 500 galaxies of the entire sample.
Makes sense.
So, yeah. So we used a double approach. The first approach was to use stacking analysis to study the average properties of the sample. And the second approach was to go deeper to study the individual sources.
Okay.
So the stacking analysis, and we go to the first. We can go to the first figure. Basically, what we did was to take all the maps in all the photometric bands from U band up to 24 micron MIPS, and do a median stacking at the radio position of the sources. So basically, of the 200 sources. So basically, what you can see is that we were stacking 200 sources. So it's like it's about 15 times deeper than the maps, the individual maps. And you can see that from B to J, you still cannot see anything. So we're talking about really extremely obscured sources. While you start to have signal from the H band, you have a significant signal in the IRAC bands and also at 24 micron. So we were able to build an SED, a median SED of this sample. For the Herschel part, we used a different approach in the sense that even if we were looking at reasonably isolated sources, our selection of, our definition of isolation was done in near infrared and IRAC bands, not in Herschel. In Herschel, it's really difficult to have a really isolated source. Exactly. So we take advantage of the Jean et al. 2018 catalog, the Super Deblended Cosmos catalog. And basically what they do in that work is to use priors, which are exactly the the 3 GHz radio catalog that we used was also used as prior for that analysis. So it's, it's really consistent. And they used these radio positions as priors, did some modeling. I will not go into the details of that paper, of course. And they ended up with the blended fluxes. So they were able to separate the fluxes of even the faintest sources. Even if of the faintest sources from detected in the radio. And basically, we took that catalog and we did the median of the fluxes. Of course, there are a lot of upper limits because even with these super deblended techniques, these galaxies at high redshift are really faint. So basically, we used a survival analysis approach to take into account all the upper limits when we derived the median fluxes in the Herschel bands. But you can see that even adopting this approach, there are still some bands where even in the median we have upper limits. So again, we are talking about sources that are at the limit of many of the current facilities. And as you can see, the result of our median analysis, we did an SED fitting using the Markfish code by D'Acunha et al. And basically, the median properties of this sample are that the sample should be centered around a photometric redshift of 3. So we are for sure selecting a large number of high redshift sources, so there must be around 50% of galaxies above redshift 3. It is also interesting to notice that we are also selecting galaxies that have a lower redshift, so we are also selecting extremely obscured galaxies that are not just faint because they are at high redshift, but they have really a lot of dust because they are, And of course, the infrared luminosity is quite high because, we are talking about extremely dust galaxies. So we have infrared luminosity of the order of the 10 to the 12. And also the average extinction that we derive from the SED is of the order of 4. So these are the median properties of the sample that we derive from the stacking. We also used the stacking to tackle the AGN problem that I was mentioning before. And in particular, we did an X-ray stacking of the 200 sources to see if we could, if there was a significant X-ray signal. And we didn't find a significant X-ray signal. The average X-ray emission that we find from the stack is consistent with being originated only by star formation.
Okay.
So that does not exclude that in our sample there are some obscured AGN, because in that case the X-ray wouldn't tell. But we shouldn't be so much biased We also did an additional test, which is not shown in the paper because we did it after the acceptance. So, I mean, we actually were looking at the radio excess. So at the radio luminosity with respect to the far infrared luminosity. And actually, which is also an indicator of AGN presence. And actually, we didn't find sources with a strong radio excess. So there should be an additional proof that we are not too much biased by powerful AGN.
Okay.
I mean, I would say that these are the main results for what concerns the stacking analysis. But then, of course, we wanted also to see if we could derive the properties of some of the individual sources. So actually, we went back to the maps. I mean, we had already a lot of catalogs from, of course, from the Cosmos collaboration. There are a lot of ancillary data, but there were also maps for which there are not yet public catalogs, but the maps are public. So we went to the maps to see if there was some, I don't know, marginal detection for our galaxies in the IRAC bands, in the near-infrared bands, even at an individual, for the individual galaxies. And out of the 197 galaxies of our sample, we actually found that for the majority of our galaxies, we could build, let's say, a tentative SED, in the sense that we could find, apart from the radio detection, between 3 and 7 photometric points, which seems too low a number to derive a reliable SED when you are working at redshift 2. But when you are working at redshift 6, is really wonderful.
Yes.
So basically, I mean, we also attached the far infrared points from the Super Blended catalog, and we went on to study more in detail the sample of galaxies which had at least 1 point in the far infrared, in order to have some constraint on the dust part. And we did again an SED fitting on these galaxies, which are about 100, so about half of the sample. And we derived the redshift distribution that is shown in figure number 2.
Figure 2.
Yeah. So yes, in red, there is the redshifted distribution of this sample, which we called primary sample. So again, this is a sample, this is the subsample of galaxies where we could find at least one detection in far infrared, and of course, at least one detection in one of the near infrared of mid infrared bands. And I mean, one very nice thing is that the distribution peaks around redshift 3, which is the redshift that we derived from the stacking analysis. So it is nice when things are consistent. But and as I was saying before, we see that we have, of course, the majority of the sources are around redshift 3. But we also have a relatively large number of sources, 22, at redshift higher than 4.5. So this is, yes. So this is really where the starting interest was for this work. So to see how are things at these redshifts. And so. I mean, of course, the redshift is just one element. The other important element to derive the star formation rate density is the star formation rate. And that's why we wanted to have at least one far infrared point in our primary sample, because basically we derived our star formation rate from the infrared luminosity. So we did again an SED fitting on the individual sources, and there is actually in figure 5 and 6 there are some examples of all the individual SEDs.
Yeah, it's all figure 5.
Yeah, so I mean, as you can see, there is a certain, there is a certain diversity in the number of points that we have for each galaxy. For example, there is this galaxy, the first in the second row, where we have a lot of points in the far infrared and only 1 point in the near infrared bands, in the IRAC bands, sorry. There are other galaxies where things are more complicated. For example, the last one of the third row, there is a probability distribution function. In each plot, I show not only the SED, but also the likelihood of the photometric redshift. And you see that here, it's difficult to say. We have a peak around redshift 5, but actually the distribution goes from redshift 2.5 to 7.5. Yeah.
Oh,
so in other cases, we have thinner probability distributions. So, but the point is that we can have an estimate, at least an estimate of the photometric redshift of these sources, and I think it is also we decided to use the MAGFIS code to do this because we wanted to use all the information from the entire wavelength range that we had at our disposal, so from the optical upper limits to the radio emission. And so I would say that, our redshifts are not perfect, but probably the best that you can have for these sources at the current status of the observation. So, and here I just plotted the sources at redshift higher than 4.5, and the highest redshift one is the last one, which is at a tentative redshift of about 8. But again, we have very few points for this one, so it's really hard to say.
Right. A lot more upper limits on that one.
But we used, of course, these the photometric redshifts and the infrared luminosities derived star formation rates to derive the star formation rate density, which was the initial objective of our paper. And the results are plotted in figure 4, exactly this one. So basically, since we had we didn't have a lot of sources, especially if we compare our sample to, if we compare our sample to samples of very high redshift galaxies, it isn't so bad. We have, I wouldn't say a lot of sources, but a decent number. But if we compare our sample, of course, to, I don't know, to the radio parent sample analyzed by Novak, for example, of course, we don't have many sources. And so we decided not to use the approach of computing the luminosity function and then integrating it. Okay. Because we didn't have enough constraints to do that. We would have to rely on too many assumptions on the shape of the luminosity function and on the extrapolation at low luminosities. So we decided just to to compute to add up the star formation rate that we were seeing. Okay. So our estimate is a lower limit, let's say, because we are not extrapolating at low luminosities.
Yes, I'm with you. Partial, if you like. Okay.
And so our results are the red bars. And here I'm comparing it to other estimates of the star formation rate density. In particular, there is the famous Madao and Lilly plot from the latest, one of the latest updates, which is, as I was saying at the beginning, mainly derived from Lyman break galaxies in the high redshift high redshift regime. And I also plot, for example, in green, an update by Bowens et al. 2020, again with Lyman break galaxies. But as a comparison, you can also see two estimates from the radio and the submillimeter, which come from Novak and Gruppioni et al. And you can see that from the radio submillimeter, there is the hint that actually at high redshift, the star formation rate density is not dropping, I mean, it is not really dropping. And I would say that a very interesting result in the end of this work is that while below redshift 3, we see that our galaxies, I mean, do not have, I mean, are a very low fraction of the total star formation rate density. So at redshift lower than 3, we are not missing that much from dust obscuration. Okay. But at redshift higher than 3, things are getting more interesting because we have that the contribution to the star formation rate density of our obscured sources is between 20 and 40% the total star formation rate density derived from LBG's galaxies. Okay. So we are, let's say, missing, luckily, a good fraction of galaxies because of dust obscuration. Okay. And here I've also shown two other samples of UV dark galaxies, which are called in other ways because they are selected in other ways. In particular, there is the HST dark selected in the submillimeter by Gruppioni et al., which is basically a selection. Again, these are serendipitous continuum sources from the Alpine survey. And then there are the H dropouts by Wang et al., which are selected in another way. Again, I mean, these are selected as being H dropouts, so galaxies that are not visible in the H band, but do have a flux in the IRAC band. Okay. And this is just to show, I mean, the point, one of the main questions that remain about this, let's say, broad category of UV dark galaxies is how do these different samples overlap?
Yes.
We do not know yet, because, I mean, some of my galaxies might be H dropout or submillimeter galaxies. I don't know, because I do not have, for example, ALMA fluxes for the majority of my galaxies. So I don't know if they would be caught up from a submillimeter selection. Mm-hmm. Mm-hmm. So the point is the squares, the red bands, and the cyan circles, should we sum them up or not? Are they overlapping or not?
Yes.
This is something that that we do not know yet. So, I mean, I would say that this is the main result of the paper. That I mean, actually, we ended up finding that there is a large fraction of dust obscured galaxies at high redshift that contribute a lot to the star formation rate density. And but I mean, this is just the beginning, because we are just starting now to understand what kind of galaxy population this is.
Right, what the beast is. Very cool. Very cool. Very nice. So you hinted a little bit on the future. So where do we go, let's say, over the next 5 years with this? Are there people who are planning to do some ALMA observations of this, or are there new surveys coming up? just where's this going over the next, let's say, 5 years?
Well, for sure, I mean, we are going to need new observations. So for sure, ALMA observations, because yes, as I said, for example, for this particular sample, there are not many galaxies with ALMA counterparts, and that would be important, first of all, to understand which is the level of overlap with the SMGs, with the submillimeter galaxies population, and also it would be important to understand which are the dust properties of these galaxies, because we don't know if they have, for example, the same dust temperature of the, let's say, normal galaxies at high redshift. So ALMA observation will be for sure very important, and of course also JWST, because one big limitation of these studies is that we are missing photometric points where the mass is. So we do not have strong constraints on the mass. So having, let's say, some deep JWST data would be very important.
Yeah.
So, of course, I mean, there is a lot to do also on the theoretical side, for example, on the modeling of these sources, because again, models do not predict so many massive dust obscured sources at such high redshift. I mean, this is a problem that already came out when the quiescent massive galaxies were discovered at redshift higher than 2. So, I mean, you need progenitors. These might be the progenitors, but which are their properties. So, I mean, I think that there will be a lot to do from the theoretical side, also from the interpretation of the data. But I really hope that we are going to get many more data, especially in the submillimeter for these galaxies.
Very cool. Good. Bright future ahead for this topic. Very good. Cool. Margay, I want to thank you so much for walking us through your really lovely article.
Well, thanks to you.
All righty.
It was a really
everyone, and we will see you on the next one. Bye-bye.
Bye.